We say suction pressure. Here we say suction saturation. What's another word for that using the same way of thinking? So we could say suction pressure, we could say suction saturation temperature, but what is it really telling us? Evaporation temperature, evaporator temperature, boiling temperature. I always ask this is just an aside, but it's one of these interesting things. What's the difference between evaporation and boiling? I always wondered that. Because you look out at a lake, you look at a pond, a creek, a river, whatever, there's evaporation happening. Is it boiling? No, obviously not. That would be very dangerous. I mean, in Florida, actually, sometimes it might be. I'm not sure. It seems like it. Is it, it's not boiling, it's evaporating. So evaporation happens just at the surface and not necessarily at the boiling temperature. Boiling happens throughout the substance and occurs at the boiling temperature. So which is actually happening in an evaporator? Evaporating or boiling? It's actually boiling. So now we have to change the term to a boilerator, which doesn't sound right. But that is actually what's happening. It's actually boiling. But for sake of keeping it simple, we'll say evaporation temperature or evaporator temperature. That's what refrigeration guys will say. If you look on the Emerson E2 control, that's what they're looking at. They're looking at suction saturation, and they'll say, what's the evap temperature on that case? What is the temperature of the evaporator on that case? It actually kind of makes sense. So heuristic, what do you compare that to? Well, an evaporator is a heat absorber. It takes heat in, right? So what is the medium that it is taking heat in from? The air that's coming over it from the inside, the return air, right? Air passing over it. So what's the difference between that temperature and that indoor air? That's what we call our TD or DTD. All right, this is the rule of thumb. And I'm going to ask this as a question, and I really want to know the answer because every market is a little different. Different levels of humidity, different types of equipment. If you have 75-degree indoor air, what temperature of vapor coil, what is your suction saturation generally going to be in this market during the cooling season?
Around 45, but we were at 40, our humidity.
Okay, there you go. There you go. Yeah, so you actually do, because this is a high humidity. Is this a high humidity market? This is a high humidity market? Okay, just like us. We actually do see lower TDs, DTDs than what they say. But generally speaking, so if it's 75 degrees, then you're going to, in this market, you're going to be running more like 43 to 45 typically. There's two main reasons for that. The one is because of humidity, and this was the battle with Jim Bergman and I. I don't know if, I never actually fully demonstrated that because it was this whole thing. It was this really long process over like 6 months where he would call, like every 3 days. It'd be like, 7 in the morning, I looked down at my phone, it's Jim calling me again. He'd be like, hey Brian, you're wrong about that. It's like, okay, here we go again. And it was just a misunderstanding, and of course, I don't want to say I was right, but I was. Because in our market, we had conditions that he just wasn't used to seeing, these very high latent conditions. And that does drive up, or drive down the DTD. It drives up the evaporator temperature. But the other reason that it happens is also because we have more oversized evaporator coils than we had before as well. So that's another thing that's driving it. But it's pretty consistent. Like, it's pretty consistently going to be in that range. And it doesn't really matter much. Even outdoor temperature, that sort of thing, condensing temperature, that doesn't really drive it too much. It's really just the energy in that air is driving that boiling temperature, creating an equilibrium at around 35-degree TD, around there. We'll say between 30 and 35. And so from a heuristic standpoint, that's something that everybody can understand. It doesn't need to be a lot more complicated than that. But then we start to ask the question, and we ask very quickly, well, what are the exceptions? Well, we say right here, this only works at 400 CFM per ton typically. Here we design for 350, and then we have higher relative humidity, so it's going to be a little outside of that in most cases. But you pick up pretty quick. And old timers would say this. They would say a version of it. And it was a massive heuristic. It was a massive shortcut, which in the old R22 days, they would say, 75-degree indoor temperature, what should your suction pressure be? That's about 75, 70 to 75, right? And that just happened to work out. Like, there's a couple things like that. There's a couple little tricks with R22 that I don't know. I think it was just God smiling on tradesmen at that time. Maybe they'd been especially good for a couple decades. I'm not sure. But the same thing was true with heat pumps. You would work on a heat pump and you'd be like, well, it's an R22 system. It's running in heat. What should your suction pressure be on an R22 system? When it's 30 degrees outside. About 30 PSI. It's like, wow, that's kind of strange, isn't it? And that's literally just a coincidence. It's not, there's no science behind that. That's just how it was. But then and no wonder when we went to 410A, people were like, this stuff is the devil. It doesn't work anymore. God is now punishing us. But once you recognize that the pressure number means nothing. It's the saturation temperature, the boiling or condensing temperature that it represents that matters. On the suction side, it's the boiling temperature in the evaporator temperature. On the high side, on the liquid line specifically, it's the condensing temperature. I'm not going to read through all of these. I'll give you guys a little secret. This is like a very little known fact because it's an app that I made that I hardly told anyone about. I have this app called MechPic. It's not HVAC School. It's a separate app. It's free. It kind of like how MeasureQuick, how Jim Bergman said MeasureQuick would always be free, and then now it's not free. This will actually always be free. So that's a little dig at Jim there. So it's still free, but but MechPic is free, and what it is where I've uploaded all of my photos of everything that I've ever done, and I have this chart on there, somewhere on there, or a version of it, that goes through each of these faults and the symptoms for each fault that you have. At some point, I'll put that into kind of its own app in HVAC School, but for now, all those images and illustrations and all that exist there. And you can even add on there, you can take add an arrow to it and add some words to it, like, hey, look at this dummy or whatever. If you want to send it to folks that you're interacting with to do training, that's what it's for. It's so that you can upload your own photos and mark them up and then share them with other people, and it's so that you can also get all of mine. And the long-term idea there is you'll be able to easily create little mini decks so you can do your own trainings and kind of voice them over. So you can be like, hey, here's a picture of a coil that's doing this and this is doing this, and oh, here's what bacterial zooglia looks like or whatever, and you can actually voice over it and it will touch indicate. And that version of that app should be out in whoever, with apps you say it's going to be out tomorrow, it'll be out 6 months from now. The point is that if you want to get into all the specific this causes that type of stuff, that's all there in that kind of full illustration. You've probably seen it before where it's got the up and down arrows and all that and the color coded. The key to all of this is just recognizing that the information, the reason why we're doing this is so that we can quickly get to the diagnosis, the troubleshooting portion as quickly as possible, so that we get the main answer, the main thing that's wrong, so that we have enough time to do the rest of it. Which those next rest of it are just as important, if not more important. So now we figured out what's wrong. Now what caused what's wrong in this particular case, and then what else needs to be optimized in this system in order to make sure that the customer gets the full benefit. The rule of thumb quickly on condensing temperature, we call it CTOA, which I'm pretty sure is an acronym that we made up. I don't think I've read that in any books. Maybe I have. It might have come from Dick Wurs, I'm not sure. But 15 to 20 degrees CTOA on modern systems is pretty typical. It's much more fluctuating than what you see on evaporator temperature, but that just simply means that your condensing temperature is going to generally be 15 to 20 degrees above your outdoor temperature. When I first started in the trade, that whole 30 degree over ambient head pressure, that's actually the way that I was taught to charge systems when I was in trade school. They didn't teach me superheat and subcool. They taught 30 degrees over ambient discharge. That's the standard way that they taught it. And in refrigeration, that still holds true in a lot of refrigeration systems. You'll still see refrigeration systems that have that level of CTOA. Just a quick question. We're going to jump like 37 levels ahead and ask the question, why do we care if our head pressure is higher than it needs to be?
Compression ratio will be higher.
Compression ratio will be higher. That's exactly the answer I was looking for. So go ahead, keep going. Do you want to stand up here and I'll give you the microphones?
Well, they pay you, Joe.
Yeah, it's not much. No.
Check, right?
Yeah. No, it's compression ratio, right? It's the same reason why having a suction pressure that's lower than it should be is a pretty significant problem as well. Because the higher the difference between your absolute suction, so your suction pressure plus your atmospheric pressure, divided into your discharge pressure plus the atmospheric pressure, so total discharge. The bigger that ratio, the greater that ratio number, the harder, the way, the silly way we'll say it is we'll say the compressor's working harder. Well, compressors don't care if they work harder. That's not the issue. But what it is that it's running hotter and it's moving less refrigerant through it. So the techie way of saying that would be it has a lower mass flow ratio. If you have lower suction pressure, the refrigerant coming into the compressor is lighter. It's less dense, so every stroke of that compressor, every oscillation of that scroll takes in less refrigerant, and the greater the back pressure that it has to push against, the more force is required, the more energy is required, and the less of it moves. That's what it comes down to. When we have higher head pressure, from a very practical standpoint, the easiest way to think about this, another heuristic, is high compression ratio equals compressor not moving as much refrigerant. So kind of obvious it's not going to perform as well. So why, when you look at the performance charts on a piece of equipment, the amount of BTUs that it moves, on hotter days, if you look at the performance charts, it moves fewer BTUs. Why? Because the head pressure is higher, compression ratio is higher, compressor's moving less freon. If you're going to call it freon, that's fine with me. It's moving less refrigerant, right? Pretty simple. And when we can get to that level as technicians, boom, 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 this, that, this, figure out main cause, figure out what could have caused it, anything else, go through that list, and then get it fixed, get to optimization. Now, not only are we a good technician in terms of the technical side, but we're also a good technician in terms of the efficiency side, and that's the goal. Have you met the guys who brag about how many service calls they do in a day? I'm sure none of you ever do that. You know, you get guys going on, and it's like, well, I've done 12 in a day. And
Callbacks.
yeah, right. Does anybody know the next phrase that somebody says after somebody says, let's just say it's a junior guy who walks into a group, he's like, man, I did 8 service calls yesterday. What does the other guy say? He says, well, that's nothing. That's the next line. It's just like if you go and you load up the back of your truck. Say you put a grill in the back of your truck or a load of lumber or something like that, and after you get done ratchet strapping it down or whatever you do, what do you say immediately after you've done that? That ain't going nowhere, right? If you don't do that, the universe turns into a vacuum and turns in on itself and implodes. Okay, it is required. It's sort of like if you're going to grill some meats, you know, so you're in it's summer and you're going to do some grilling, and you get it all out. What's the first thing that you do? You go click, click, right? You have to do that. If you don't double click the tongs, the food will be poisoned. We know this, right? It's just like that. Guys love to one-up each other. That's the point. Well, that's nothing. It's like telling somebody that you had one wisdom tooth pulled. This is a joke that I'm stealing from somebody else. But you tell somebody that you have one wisdom tooth pulled, oh man, and just wait. That's nothing. I've had 4 wisdom teeth pulled, whatever. I've had 8. I've had 10 wisdom teeth pulled. It doesn't matter. But it's the worst possible thing to be proud of, right? Why are we proud on how many service calls we do in a day? That is a silly thing to be proud of. What we should be absolutely proud of is that we did an efficient job, meaning we used our time wisely, we served our customers well, and we not only fixed the problem, we fixed the cause of the problem, and then we optimized some people's systems. That's what we should be proud of, and whether that's 4, 2, 6, 3, 8, I don't care what it is, if that's what you did, then that's something to be proud of. You mentioned callbacks. Oh my goodness. Let me tell you, if it wasn't for callbacks, I would be at least 1,000 there. Possible causes of improper head pressure. That's another key one. Is it possible to have head pressure that is too low? Is that possible? Depends on what you mean by it, but sure, it is possible to have head pressure that's too low. Perfect example is a couple years ago there were these cold snaps that went through Chicago, and all the market refrigeration guys had just absolute nightmares because outdoor temperatures were -30, -40 degrees in that market. And all the grocery stores, your head pressure, literally, you think of this, the outdoor temperature is significantly lower now than what you want your lowest box temperature to be inside the store. In order for matter, a substance, to move from one place to another place, what has to be present there? Right. I mean, we can say pressure difference, but there has to be, at very minimum, a difference in energy state. I mean, even if I take it and shove it from here to there, I'm adding energy to it to move it from here to there, right? How are we going to get refrigerant to move from low pressure or from low pressure to higher pressure? How are we going to get that to happen, right? There is a point at which it becomes a problem, like because we got to figure out how to get stuff moving the direction we want it to move. That's really what we do in this trade. We're trying to get refrigerant to move the direction we want it to move at the temperatures that we want it to be at the different points. I mean, that's really what we're doing here. So yeah, it is possible to have head pressure that's also too low. But again, we say too high, too low. What we're really saying is, what is causing this system to run in a way that's not its design. Because we're not going to make a system to run better than the engineers who designed it, probably. I mean, I guess it could be possible. But they designed it to work a certain way. We're trying to figure out what's outside of the design here. Just like capacitors, they're designed to fail every 3 weeks, apparently. TXVs, they're designed to all be bad, apparently. I don't know. I just replace the TXV. Every time I do a maintenance, just replace the TXV. You know, just be safe. Just throw a no one in there, no problem. Just replace the TXV. That's a joke. I'm kidding. Don't take me seriously. Superheat. We're going to talk quickly about it. What is superheat really telling us? What is it indicating to us about the system? Amount of liquid that's in the evaporator. Yeah, that's a really good way of thinking about it. That's the way that I talk about it in the videos. Imagine a refrigerant stacked in that evaporator coil. How full is it? And when you think about this, again, as a heuristic, our suction saturation, our evaporator temperature, tells us the temperature of the evaporator, and our superheat tells us how full it is. You know those two things, now you know what you need to know. You can't just know one or the other because that doesn't tell you enough. You could have a 10-degree superheat and an evaporator temperature that's way lower than it should be or way higher than it should be, and that's still a problem. But if you think of it in terms of evaporator fullness with liquid refrigerant or saturated refrigerant, that's a good heuristic to use. Is it exactly right? Well, I mean, yes and no, because there's another major problem. When somebody says my superheat is 10, somebody calls you up, what's your superheat? Superheat's 10. What should be the next question? I just heard a lot of different answers there. My next question.
How much money they got? Can we sell money?
Yeah, how much money you got? Yeah, what kind of cars you got in the driveway? It's a Bentley? It's a bad system. No. The next question would be where? The where question in superheat gets missed a lot. Because is it possible that my superheat at the evaporator coil and my superheat at the condenser or at the compressor could be significantly different? Is that possible? Yeah, definitely. Now, is it possible on the liquid line too? Yeah, it is. But generally speaking, it's not going to be nearly as much of a spread. But it's very possible, because where are we typically measuring superheat? Out of the condenser, right? We're measuring at the same place that we hook up gauges. And, you know, back in the day, I remember going to this train, I think it was a train class, and they were talking about this topic. And the instructor, the instructor said something about evaporator superheat, and it was me or somebody else. I don't remember, it's probably me, because I was always a mouthy kid at that time. And it's like, well, how do you measure it in the inside if you can't put pressure ports there? And he said, well, you should put pressure ports there. I'm like, what? Yeah, you pump down the system, put pressure, like, what are you talking about? I mean, that's ridiculous. So we know that we're gonna measure our superheat realistically at the condenser most of the time. But if we have 20 degrees of superheat outside at the condenser, is that good or is that bad? It's probably good, but we could have an evaporator coil that's, if the superheat's 20 outside and 20 inside and you only got 10 feet of line set, that's pretty low. Pretty high superheat for an evaporator superheat. So the next question is, are we talking about compressor superheat? Are we talking about evaporator superheat? Because, you know, Copeland says they want 20 degrees of compressor superheat. They want your superheat to be 20 degrees at the compressor. They'll tell you that less than that's actually a problem in many systems. Knowing where is pretty significant. What is the job of the TXV? Let's get into TXVs real quick. Set superheat, right? And where does it set it? The end of the evaporator. It could be setting the superheat to 10, 12, 14 at the end of the evaporator coil, meaning controlling the fullness in the evaporator coil. Again, go back to heuristics, shortcuts in your brain. Controlling the level of the refrigerant in the evaporator coil. It could be doing that really well, but then we can measure on the outside and say, my goodness, we got 30 degrees of superheat, we've got a bad TXV. Two favorite words in the trade. But the TXV only has control right there. Can the TXV control superheat if there's a plugged liquid line dryer? No. Can the TXV control superheat if you have zero subcool and you got flash gas in the liquid line? No. The TXV's job might be to control superheat, but if it's not given its prerequisites, then it can't do what it's supposed to do. And that's the problem with that statement in terms of a diagnostic term. So the TXV's job is to control superheat if everything else that we just mentioned is controlled for. We're measuring it at the evaporator coil. We have a full line of liquid, i.e. we've got subcooling, we've got the design subcooling, and we don't have any sort of significant line restriction. I'm gonna give you for those of you who are more advanced and are about to fall asleep on me because I'm seeing some of you, is it possible to have a significant liquid line restriction. Okay, you with me here? Significant liquid line restriction, say a line dryer, and have no temperature drop across the liquid line dryer or across the restriction. Is that possible? So I'm saying a significant pressure drop, and under what circumstances is that possible? Yes, you could. It could be no flow whatsoever, theoretically. But let's say that we do. I mean, that would be pretty rare. Let's say that you do have flow. I said no, and I said no in front of a class of people about this size. I said that you would always have a temperature differential, and this is a long time. Does anybody here know Joe Shearer? Anybody ever bumped into him? He's on social media and all that. He's a great guy, but he's also a troll. So he's one of these guys who he'll just put something out there, and he'll let you just dangle. You know, he's got the answer, kind of like I'm doing right now. He's got the answer, but he's just going to let you dangle, and he's going to let you say the wrong thing and look stupid, and then he'll tell you otherwise. What he pointed out to me is that if you have excessive subcooling, like massive subcooling, where somebody kept putting charge in it or whatever, and you have a pressure drop, it can actually eat up that subcooling before it gets to actually flash gas. And you can actually have a case where that entire assembly there is full of liquid, and you don't get a temperature drop. Because getting a temperature drop on liquid with pressure alone, see, I always thought that you did. I thought, well, and I even say this in one of my videos, decrease in pressure equals decrease in temperature. Increase in pressure equals increase in temperature. On liquid, while that is technically true, it's something like 0.00001 degree. Like it's immeasurable. You're not going to measure it. Are there cases where you could have no temperature drop across the liquid line dryer and actually have a plug dryer? And the answer is yes. Because you would say, well, yeah, but if I had 30, 35, 40 degrees of subcooling, I would know that I did, right? Because I'd hook up on my port and I would see it. Well, there's a couple brands of equipment where the line dryer is on the inside of where you're measuring the pressure. So you're measuring it past the dryer. Get what I'm saying? Goodman? You know, you've seen these, right? It's got the liquid line dryer inside the condenser. Those happen to be the ones that plug up all the time too. Might have to do with the fact that, you know, Goodman installers, you know, little different breed, but we won't talk about that. Anybody here sell Goodman? Just kidding. I'm just kidding. I'm just kidding. We sell Goodman. Nothing wrong with the equipment, just the installers. I'm just kidding. You'll get those, and because you're measuring past it, you may say, well, I've got 5 degrees of subcool out here. I've got no temperature difference across the liquid line dryer. It's not the liquid line dryer, but it actually, there are cases that it can be. Now, your first indication is that the compressor sounds like, you know, it's screaming because it's got head pressure in there that you're not measuring. If you check your current on your compressor, you'll see really high current, like abnormally high, because the thing's got compression ratios through the roof. That would be your indication. But other than that, it's actually really hard to know. And there are these cases like this that you'll run into. So again, subcooling. What's the purpose of subcooling? Yes, tell us exactly. How much of a stack of liquid column is there in the condenser? Lower subcool means it's starting to get empty. Higher subcool means there's more liquid stacked in the condenser. Are there systems that don't really require subcooling? Yeah. Refrigeration systems that have receivers don't hold refrigerant in their condenser. The condenser does not stack refrigerant. Liquid refrigerant goes through the condenser, these droplets, they condense, and then where do they go? They just dump into the receiver. And the receiver holds the excess refrigerant. So in an air conditioning system, the ones we work on that are receiverless, we're using the condenser to store liquid. But in a grocery store refrigeration system, which we work on all the time, you have so much variation in load in terms of some days you may have one case that needs refrigeration, and you have the whole rest of them that don't. Or a hot day versus a cold day, or a high load versus a low load. They're filling the cases versus not filling the cases, that kind of stuff. So you have to have massive amounts of backup refrigerant, liquid refrigerant stored. And so in that case, you don't necessarily have subcool. So what is the purpose of subcool? When we measure it, it tells us that, right? But why do we care? Because we want to know, are we feeding our metering device with a full column of liquid? Full stop. A lot of people will do this whole thing where they say, more subcool equals more efficiency. It's a tricky thing. Because when you increase the charge in your system, so you take a typical system that you guys work on every day, whatever you sell, right? And you it's like, all right, my subcool's low. I'm gonna get my subcool up. And you add refrigerant to the system. Are you decreasing the liquid temperature, or are you increasing the condensing temperature? See, when we say we're getting more subcooling, what are we thinking we're doing? What do we imagine in our head? We're imagining we're making the liquid colder coming out of the condenser, right? But there's two sides to that math equation. That math equation has condensing temperature on this side, and it has liquid temperature on the other, right? So we can increase subcooling by dropping liquid temperature, by increasing condensing. Some cases there might be a little bit of a drop in liquid temperature, but it ain't gonna be much. Most of that increased subcool, once you have subcool, is gonna be caused by increasing your condensing temperature. So it's a trade-off. We actually don't want high subcool, because what are we doing to our effective condensing area in our condenser? Making it smaller. We're stacking liquid in that condenser. Now the area that actually does the condensing gets smaller and smaller, right? We're giving ourselves a smaller condenser the more subcool we get. Is this ringing a bell with anybody?
Yeah, my guys, I put a piece of cardboard on the condenser. You're losing that.
Right, that's what you're doing. You might as well be blocking the condenser off. You might as well be throwing some dirt on it. You know, and it's like, hey. All right. So when people say, with every degree of subcool added, the efficiency increases by 1% or whatever, they'll say things like that. What are they saying? Why are they saying that first? There's two ways that they're correct, and one way that it's a lie. The one way that it's correct is if that additional subcool is resulting in proper liquid quality at the metering device before it didn't. Meaning that if we had 10 degrees of subcool, we have 10 degrees of subcool, and now at the metering device, we've got 3 and we've got good liquid quality, versus having 5 degrees of subcool and now having flash gas at the metering device, yes, that is increasing efficiency. Simple terms, we need to feed our metering device with a full column of liquid. Full stop. But if we do that by increasing our condensing temperature artificially, that's a bad thing. Now, here's another way that it's a good thing. If we are increasing subcool by dropping our liquid temperature. And how could we do that? Mechanical subcooling. Now, we don't do that very often in residential air conditioning. But in grocery stores and other areas, what they do is they literally mechanically cool the liquid. So they make it liquid, and then they run it through an evaporator heat exchanger or something like that, and they cool it some more. Well now, yes, because now when it goes to that evaporator coil, it takes less energy to change it initially to flash it off. You know how we say, some of you have heard when a liquid goes into the evaporator coil, it immediately goes to 30% vapor, 70% liquid, some version of that. If you cool that liquid down more, then you lose less to flash gas conversion as a percentage. So is that something that you could do? Sure, we don't in air conditioning much, but you could. So when people say that, sometimes that's what they're talking about. They're confusing information. But other than those two things, making sure we have liquid quality, having enough subcool so it makes it up the wall and through the attic and all the way over and over the river and through the woods, and then it hits the metering device with liquid. Or if you're mechanically cooling it, other than that, increasing the subcooling does not help. It's not a good thing. It's just like saying, and you've all had this happen, new kid goes to a job, Mrs. Smith is complaining that her house is not cooling properly in the middle of summer. My house is not cooling. You put this new system in and it hasn't cooled right since you installed it, right? They don't all talk that way, but I shouldn't make poor Mrs. Smith sound that way, You are, blah, 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 blah. That's in Groveland, Florida, that's what they sound like. New guy goes out and he calls you up and he says, boss, I fixed it. Well, what'd you do? Well, I adjusted the charge, right? I got it where before we had 5 degrees of superheat, and now we have what we're supposed to have, we got 10. So I solved that problem, right? Now again, this was back in the day when you had fixed metering devices and you were actually setting superheat by setting the charge. But if we have an evaporator coil that we were filling this much with boiling refrigerant, and now we're filling it with less boiling refrigerant to hit a number that the manufacturer gave us, did we improve the efficiency? The answer is no. Now, the manufacturer gives us that number for a reason. And so it's good that you adjust the charge to hit manufacturer specs. But if the goal was to try to get her more capacity out of the equipment, that did not solve the problem. In the same way that when the new guy goes out nowadays and he says, I fixed the problem. It only had 7 degrees of subcool, and I adjusted to what the manufacturer said, which was 11. Now we're good, right? No. You actually made the system perform worse by doing that. Now, if that's what the manufacturer said that you need, then good on you. I'm glad you did it. But you didn't improve the capacity of that piece of equipment unless it was resulting in flash gas at the metering device. Make sense?
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.